Hi everyone, I'm Charmaine from Group 2 and we are here to discuss logical design. What exactly do we mean by logical design? In the last module, we learned about the conceptual data model where we map entities, attributes, and relationships into an entity relationship diagram. Logical design is the process of transforming that conceptual data model in a logical database model. A logical database model is a design that conforms to the data model for a class of database management system. Can you remember the different data models discussed in the previous module? Let's recap. We have the hierarchical, network, and relational models. This module will focus on the relational data model. There are two phases in creating a logical design of a relational data model. First is transforming the conceptual model to a preliminary logical data model. And second is optimizing the logical data model by applying the rules of normalization. Our group will only cover the first step. In a relational data model, relation is the most important construct. It is a named two-dimensional table of data which consists of a set of named columns and an arbitrary number of unnamed rows. Here, we have an example of a relation employee. The attributes employee number, name, department, position, and extension number form the columns. The number of attributes in a relation is called the degree. A row in the relation is called a tuple and represents a particular employee entity. The number of tuples in a relation is called the cardinality. The primary key in this relation is the employee number. It serves as a unique identifier for the table. It is possible to have two employees with the same name, department, and position, but it is impossible for both to have the same employee number. Null values in the tuples represent attributes which values are unknown or does not exist. Next, we have the relation schema, which is used to describe a relation. A relation schema R, denoted by R, parentheses, attribute 1, attribute 2, attribute 3, and attribute n, is composed of the following: relation name R, and a list of attributes. In this example, the relation can be described by the following schema: employee, parentheses, employee number, name, department, position, extension number. Up next, EJ will be discussing the properties of a relation.
Hi, can we consider every table data a relation? The simple answer is no. Relation has a property that distinguishes them from any common table. Let us discuss those properties. First, we have column are atomic. Values are atomic. This property implies that the column in a relational table are not repeating groups or arrays. Such tables are referred to as being in the first normal form. The atomic value property of a relational table is important because it is one of the cornerstones of a relational model. The key benefits of one of the property is that it simplifies data manipulation logic. In our example, the name of column should contain the name of individual, person, and not the list of person's name, like this one. Next, we have columns are from the same domain. Column values are of the same kind. In the relational term, this means that all values in column come from the same domain. A domain is a set of values which a column may have. For example, let's say that the data type for employer number is an integer. Therefore, all entries from this attribute should be an integer. This property simplifies data access because developers and users can be certain of the same data contained in the given column. It also simplifies data validation because all values are from the same domain. The domain can be defined and enforced with the DDL, as we call as the data definition language of the database software. Like this one. This is shown as an example of same domain. Next is each row is unique. Each row is unique. This property ensures that no two rows in a relational table are identical. There is at least one column or set of columns, the values of which uniquely identify each row in the table. Such columns are called primary keys and are discussed in more details in relationships and keys. This property guarantees that every row in the relational table is meaningful and that a specific row can be identified by specifying the primary key values. Next, we have sequence of column is insignificant. This property states that the ordering of the column in the relational table has no meaning. Column can be retrieved in any order and in various sequence. The benefits of this property is that it enables many users to share the same table without concern of how the table is organized. It is also permit that the physical structure of the database to change without affecting the relational tables, like this one. Next, we have the sequence of row is insignificant. This property is analogous. The one above but applies to row instead of columns. The main benefit is that the row of the relational table can be retrieved in different order and sequence. Adding information to a relational table is simplified and does not affect existing queries. Next, the last property is each column is unique. Because the sequence of column is insignificant, column must be referenced by name and not by position. In general, a column name need not to be unique within the entire database but only within the table to which it belongs. So remember, not all table is a relation.
Transforming entity relationship diagram to relation. There are two steps in transforming a conceptual data model to its equivalent preliminary logical model. First, representing the entities, and second, representing relationships. Step 1. Representing entities is the easiest step in the logical design phase. First, we need to create a relation whose number of columns is equal to the number of attributes associated with the entity and give the relation the name of the entity type. For each entity type E in the ERD, create a relation R that includes all the attributes of the E. Underline column implies that it contains the identifier or the primary key of the relation. Any attributes which contain a value that corresponds to an attribute value in another relation is called a foreign key. It is desirable to use the same attribute name in both relations. A foreign key is underlined using a broken line. Let's take a look at our sample ERD. The entity customer will be our relation customer and its attributes, customer number, name, and address will be the columns. Notice that customer number is underlined by a solid line. This means that the customer number is the primary key for this table. If we are to add this to another relation as a foreign key, we distinguish it by underlining with a broken line. Step 2. Representing relationship. The second step in transforming a conceptual data model to its equivalent preliminary logical model is representing the relationship. This step depends on both the degree of the relationship and its cardinality. Can you recall what are those? Degree of a relationship is defined as the number of entity types that participate in a relationship. A relationship with a degree 1 is called unary or recursive. A relationship with degree 2 is binary, and one with degree 3 is referred to as a ternary. The cardinality or cardinality ratio in a relationship specifies the number of instances of an entity type that can be associated with an instance of another entity type. We'll discuss how to represent the entity type of the relationship as follows: binary, 1 to n, binary, 1 to 1, binary, m to n, unary, 1 to n, unary, m to n. But before we proceed to that, let's review the different notation and their meanings so we can understand the minimum and maximum cardinalities of the relationship between entities in the upcoming samples ERD. So here's the sample notation and their meaning. Are you done reviewing? Then let's get to the first type of relationship.
Thanks, Carl. Hi, my name is Christian and I will be discussing the representation of relationships. To continue, let me start with one-to-many relationships. If two entities are maintaining a one-to-many relationship, we can simply add the primary key of the one-side relation as foreign key in the many-side relation. In our sample ERD, we have two entities having one-to-many relationship, customer and order, which have the relationship places. A customer may have 0, 1 or many orders, while each order must be placed by one customer. After transforming each entity to a relation, we have these two tables. To represent the relationship between these two tables, we can simply add the primary key customer number from relation customer as a foreign key to the relation order. The relation order will now have the schema order with the fields order number, date, and customer number. The next one is the one-to-one relationship. If two entities are maintaining a one relationship and can share the same primary key, they can be represented by combining the two entities into one. Attributes of entity B will be moved into A and a common primary key will be established. In our sample ERD, we have two entities, passenger and passport, which has one-to-one relationship. A passenger must have a passport and each passport must be owned by a passenger. If we transform the entities to relations, we'll get the following. To represent the has relationship between them, we can simply move the attributes from relation passport to the relation passenger. The relation schema would then be passenger with the fields passenger number, name, address, passport number, and expiration date. These are instances when this would not be admissible. For example, one of the entities participate in more than one relationship. In those cases, we can represent the relationship either by adding the primary key A as foreign key of B. Next is adding the primary key of B as foreign key of A, or both of the above. Representing a many-to-many relationship between two entities requires creating a separate relation. primary keys of relation A and B will be included as foreign keys in the newly created relation, and its combination will form the primary key. If the relationship has an associated attribute, for example a quantity, we should be including these as attributes in the new relation as well. In our sample ERD, we have the two entities, order and product, having the relationship has. Each order must include one or many products, while each product can be included in 0, 1, or many orders. Let's translate the entities into relations. Now, let's form a new relation to represent the relationship has. So we have these participating entities, order with order number, date with product, product number, and description. The relationship attribute will be the quantity. We can form the new relation which will have the following schema: order list with the following fields: order number, product number, and quantity. The combination of foreign keys from relation order and product forms the primary key of the new relation order list. A unary representation of one-to-many relationships is an entity having a one-to-many relationship with itself and can be represented by simply adding a rename of the primary key with reference to the relationship. In our sample ERD, we have the entity employee, which have the recursive one-to-many relationship manages. An employee is managed by one manager, and an employee can manage 0, 1, or many employees. Transforming the entity into a relation, we will get this. To represent the relationship manages, we can simply add a rename of the primary key employee number to the relation. In this case, we can rename it as manager underscore ID, which will contain the employee number of the employee's manager. For unary many-to-many relationships, we need to create a new relation representing the relationship similar to binary many-to-many relationship. We need to include the primary key of participating entity as foreign key in the new relation. Since there is only one entity, we need to include a rename of its primary key as foreign key to the new relation 2. In our sample ERD, we have the entity item, which has the many-to-many relationship contains. An item can be an item by itself or contain one or more other parts, and an item can be part of 0, 1, or many items. Let us transform our entity into a relation. Now, let's form our new relation. So we have the relationship contains. The participating entity is the item with the fields item number, name, and cost, and the relationship attribute is quantity. Now we have this new relation schema, the item underscore bill, with the following fields: item number, part number, and quantity. The primary key of relation item and its rename were included as foreign keys in the new relation item underscore bill. These two forms the primary key of the item underscore bill relation. For better understanding of the terms used, binary relationship is when there are two entities involved in a relationship degree, while the unary relationship is when both participants in the relationship are the same entity. Logical design is the process of transforming the conceptual data model into a logical database model. That's it for the logical design group, and we hope you learned a lot from our discussion. Thank you for watching.